Hello and welcome to the micro lecture on fairness in machine learning. You will learn to define fairness in machine learning, and you will be able to explain why it is especially important in high-stake domains. You will identify and compare different fairness metrics, and you will be able to recognize the limitations and incompatibilities of those. You will comprehend that bias is the opposite of fairness, and you will be able to recognize its various forms and sources. You will also learn about bias mitigation strategies and to understand the ethical and contextual dimensions of fairness. Subsequently, we will start with the definition of fairness in machine learning, then we will talk about fairness metrics, bias, forms of bias, bias mitigation strategies, and ethical and practical challenges. The general definition of fairness is that it is the absence of any prejudice or favoritism toward an individual or group based on their inherent or acquired characteristics. And yeah, it's very important because nowadays AI, or more specifically machine learning, has gained a lot of popularity and is used in many domains, and therefore it influences very important decisions such as hiring decisions, also decisions about lending, policing, and healthcare. And these are very important areas that already are influenced by social bias and discrimination, and we don't want that the machine learning models amplify those already existing biases. And an example would be that a biased model denies loans more frequently to applicants from a certain ethnicity due to skewed training data. So that's one kind of bias that in the past some human made the decision to more frequently deny loans to people from a certain ethnicity, and therefore the machine learning model would continue making these decisions because it just learns from the data. But that is something that we don't want. We want them kind of to act better than humans might have done in the past. Here are some examples of fairness metrics. One is the demographic parity, which means the likelihood of a positive outcome should be the same regardless of whether a person is in the protected group. We just had the example of whether or not a person is given a loan by a bank. So here the positive outcome would be that you receive the loan, and that should be regardless, for example, of your ethnicity. Then we have the fairness matrix equal opportunity, which is that the probability of a person in a positive class being assigned to a positive outcome should be equal for both protected and unprotected group members. So if your credit score is good and if you have kind of enough money, then you should be granted a loan despite of your ethnicity. Then we have equalized odds, so the probability of a person in the positive class being correctly assigned a positive outcome and the probability of a person in a negative class being incorrectly assigned a positive outcome should be both the same for protected and unprotected group members. And last but not least, we have the calibration. So given a prediction score, its meaning should be consistent across groups. So the prediction score for a certain subgroup should not be better or worse than for any other subgroup. The opposite of fairness in machine learning is bias, which is defined as a systematic error in decision-making processes that results in unfair outcomes. And it is very important to deal with bias because it can amplify already existing societal biases and also therefore increase discrimination, which we most certainly do not want. There are different sources of bias. First of all, there is data collection. So it can occur when you train machine learning models on data that are underrepresentative or incomplete. For example, if you have data about different people, and there's one subgroup of people which is completely left out from the data, then it will be very difficult to make predictions for these people because they are not in the training data. Then you have the feature selection bias, which occurs if you include or exclude certain features, for example ethnicity, that can amplify societal biases. Then you have the model design bias, which is an algorithmic choice or objective function that prioritizes overall accuracy. So yeah, basically by default, all machine learning models prioritize overall accuracy, and therefore you have to make a slight moderation so that it tries to maximize the overall fairness across subgroups. Then, which is I think the most common source of bias is human decisions. So as we mentioned, there are already existing societal biases, and they are reflected in the training data. So if some subgroup has been discriminated for years and you collect training data from these years, then obviously the bias is reflected in the training data. So then you have to make moderations or modifications to the training data to erase this bias. After learning what a bias is and how harmful it can be, we will now talk about some bias mitigation strategies, meaning how to avoid bias or deal with it when it happens. So on the one hand, you can do pre-processing, so to modify the training data before you even put it into a machine learning model. Methods would be reweighting, resampling, or obfuscating sensitive features. Then you can also do in-processing, meaning to alter some steps while you execute the machine learning algorithm. That you could do by a fairness-aware loss function, for example. Another step would be the post-processing, so you just let the machine learning model run, and then you adjust the predictions after the training. You could do that, for example, by altering some thresholds. So, in theory, all these bias mitigation strategies sound very well and suitable. However, in practice, it's often more difficult than that. There are different challenges. For example, you have the representation harm, which means that you can have stereotypical outputs even if you do not have direct bias in your data. So, machine learning models try to find important features and therefore may neglect others which already are important. And moreover, you usually have a trade-off between fairness and overall accuracy. So you have to choose which one you want to prioritize. And doing that may harm the other one. And I think a really important point is that it's very hard to define what is fair in practice, because the perception of what is fair may vary by culture, law, or even a stakeholder perspective. And last but not least, the factor explainability. So to address the complexity of human behavior and decision making in machine learning, is very difficult and therefore very hard to explain, which might mitigate fairness in another way. So what did we learn in this lecture? We learned that basically fairness is the discrimination of a subgroup. As I just said, what exactly that means in practice can depend, but that's the general concept. And I hope you are aware that it's very important to consider fairness, especially in high-stake domains, which means especially in domains that affect people's lives. And that you are able to identify and compare different fairness metrics, that you are also able to recognize the limitation and incompatibilities about fairness metrics in practice. Yeah, meaning that, for example, the trade-off between accuracy and fairness is very difficult because obviously you also want your machine model to be as accurate as possible, but that, yeah, might be decreasing the fairness of your model. You should be able to comprehend that bias is the opposite of fairness and that it has different sources. And you should be able to describe different bias mitigation strategies and especially to understand the ethical and contextual dimensions of fairness. Thank you very much for listening.